Hi folks, today we're going to be going over Algebra 2 logarithm notes. Just a note that I have severely condensed this video because of the fact that we only have 1 week left and we only need to go through what is absolutely needed to know for anyone going on to pre-calculus next year. I'm also going to be posting some things on the classroom that are extra things that will be good for anybody going on to pre-calculus to look at. But this will cover the basics of what will be needing to be known as well as that. So, logarithms, evaluating logarithms and what they are. Well, a logarithm is finding a way to find an unknown exponent when we must use logarithms. So, logarithms. And what these are the inverse of exponential functions. I'm going to run out of room here. Exponential functions. So logarithms are the inverse of exponential functions. So if we're definition of a logarithm, we actually have bases. So that means let b and x be positive numbers. B is going to not be equal to 1. The logarithm of x with base b is denoted by log base b of x. And it's going to be defined as follows. If you have log base b of x equals y, this is going to be interchangeable, so meaning you can go back and forth between the two forms of b to the y power equals x. That is probably going to be the most important concept of this entire lesson today. I'm actually going to highlight that because that's how important it is right here. So log base b of x equals y is the same as b to the y power equals x. So the base to the y power equals x. So expression is read as, right as I said it, log of y with base b. So log of y with base b. So let's go on to a couple examples here. What we're going to be doing is just switching back and forth from logarithmic form to exponential form. So here we have, we're not solving them right now. I'm just switching back and forth. So logarithmic form is log of, then we're going to be looking at 5 with base, so that should be a log of x with base b. Sorry about that. So log base 2 of 32 equals 5. Let's get on to that. So, sorry about that. 2 to the 5th power equals 32. That's exponential form. So log base 7 of 1 equals 0. 7 to the 0 power equals 1. Because we know anything to the 0 power equals 1. And finally, log base 13 of 13 equals 1. 13 to the 1st power equals 13. All right, now we're given 2 that are in exponential form, and we need to move them back into logarithmic form. So we have 6 squared equals 36. Well, again, if we look up to here, b to the y equals x. That means 6 squared equals 36 here. We need to have log with a base of 6 of 36 equals 2. Oh, got a little bit out of focus there. Come on, back to focus. There we go. Sorry about that. Not sure why it came out of focus. Okay, hopefully that doesn't happen again. 8 to the negative 2nd equals 1 over 8 squared, or 1 over 64. All right, that means we have log, and we have a base of 8 of 1/64 equals negative 2. All right, moving on. This time we have a variable introduced. So we have log base x of 25 equals 2. Well, x squared equals 25. So if we did have this, I know I said we weren't solving this, but as an example of how we would solve this, x squared equals 25, well, we know that x then would equal plus or minus 5. All right. So then we have g here. We have log base 3 of 81, but we have nothing on the right-hand side. Well, to solve this, we need to put an equals x here. Then our exponential form would be 3 to the x equals 81. All right, so that is just switching back and forth from logarithmic to exponential form. We are moving on to natural logarithms. So natural logarithms are going to be with a base e. If I was in my classroom, I'd say we have a big poster that says all the numbers of e on the poster, but I'm going to abbreviate it. It's a representation of the number of 2.71828, and just like pi, it is never ending. So this is referred to as the natural base. Natural base. In other words, it's also Euler's number. Euler's number. He is the mathematician who discovered this number. So like I said, like pi, it is an irrational number. When a logarithm has a base of e, all right, it is a natural logarithm. For example, ln is what natural logarithm looks like. Ln x, we'll say, is read as the natural log of x. All right, so let's actually find this on the calculator. If we were actually to say, ln of anything, there is the ln button, all right? And if we were going to do e to the anything, we do second, and then press that button because the e to the x is right there, ln. And, whoops, if it was on, you'd see the little e come there. We could also do ln and put any number right there. We can also do a logarithm. So log button is right there, and it would do log of a number. So you can actually use your calculator to find almost everything here. So you'll want to find that on your own calculator. All right, let's do a couple of practice problems here. And also I would like to note that ln x is also equal to log base e of x. That's what going between the two forms would look like right there. All right, so ln 50, or natural log of 50, equals x. Well, the exponential form here is, again, an imaginary e, so e to the x equals 50. All right, well, we have natural log of 36 equals 2x. Again, e to the 2x equals 36. All right, switching back from exponential form to logarithmic form. If we have e to the x equals 8, that means that ln 8 equals x. You do not have to write the e on the base for natural logarithms. All right, e to the 5th equals 10x. So that means we have natural log of 10x equal to 5. And finally, if we have e squared equals x plus 1, this is the natural log of x plus 1 equals 2. All right, we are moving on to the second part of our lesson here. And the second part of our lesson is common logarithms. So common logarithms have a base of 10. Base 10 logarithms are, like I just said, are called common logarithms. And they're usually written without the 10 base. So they're just written as log. So log x really equals log base 10 of x. And again, I've already shown you where to find this on the calculator. So most calculators have a log button, which evaluates a log with a base of 10. So in order to evaluate this any of these logarithms, it's going to cause probably a little bit of a problem, right? Because these don't have a base of 10. But that is why we have something for common logarithms called change of base. So change of base, because again, in your calculator over here, if I was to press log, it doesn't give me a base. It assumes a base 10. So I need to do something called change my base. Well, when I do that, for all positive numbers a, b, and n, where a does not equal 1 and b does not equal 1, then I have log of a, base a of n, is equal to log base b of n divided by log base b of a. This is a fantastic way to find an actual answer. So for example, if we have log base, let's see, where am I here? Oh, there we go. Log base 2 of 5, to evaluate this in a calculator, we could go log base 10 again of 5 divided by log base 10 of 2. So log 5 divided by log 2. What does that look like? Well, if I was actually, I'm going to pull my calculator over here now. I have log 5 divided by log of 2. And I would get about or approximately 2.32. All right, so helps you evaluate logarithms that do not have a base of 10. Yay! Now, some calculators, some calcs, have a log base button. This is not all calculators, but some do. This is a very helpful little button. So, like I said, we use change of base to evaluate this logarithm. My calculator, I could also do math, and I could go up to log base, press enter, and then I could actually put my log base 2 of 5, and I would get 2.32 again. So some calculators do have that, and again, that would be math, and then log base, and then you would enter the numbers. So that'd be how you would go about doing that. All right, let's practice on here. So using a calculator to evaluate the following logarithms. Here, this would be equal to log 3 divided by log 9, which is 1/2. This would be equal to log 8 divided by log of 1/8, which if I were to evaluate this, it would be -1. I've already previously evaluated these, so you can definitely pause this video if you want to do it before me and see if you are correct. Here we would have log of 1/9 divided by log 3, which equals -2. And here we have finally log 1 divided by log 15, which would equal 0. All right, our last thing we are going to go through is solving logarithmic equations here. And so we are going to let our b value be greater than 0 and b not be equal to 1. So on your sheet, this will be correct here, but log base b of x will equal log base b of y if and only if x equals y. All right, so if we have two logarithms with exact same base, to solve, we can set these equal to each other. That means that we're going to set x squared equal to -6x minus 8. And we need to make this into a quadratic equation. So we're going to have x squared. We're going to add 6x to both sides. We're going to add 8 to both sides, and that's going to be equal to 0. Solving this, again, you could use our x factor here, our x box as we call it. 8 goes in the top, 6 goes in the bottom. We're looking for two numbers. Those two numbers are going to be 4 and -2. So, I'm sorry, 4 and 2, not -2, my bad. 4 and 2, so we have x plus 4 and x plus 2 are going to be equal to 0. And that means x's are going to equal -4 and 2. Last thing you need to do is check these answers. And so if you were to check them, they actually do work out. That would be, again, log base 4 of negative 4 squared would equal log base 4 of negative 6 times negative 4 minus 8, and the same thing for negative 2. Both of those happen to work. Trust me, I don't want this video to be any longer than it has to be, so they do work. All right, our last one here. Both have base 5, so that means we can set what is in the parentheses equal to each other and solve. All right, adding 2x to both sides and subtracting 1 from both sides, we get 7 equals 5x. And dividing by 5 on both sides, that gets us 7/5 equals x. Again, you would want to check this, and I promise you it works. That is our lesson. Have a wonderful night, folks, day, wherever you are at. And thank you for listening to the last lesson of your Algebra 2 career in 2020.